What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this: a vast, endless expanse of darkness, dotted with shimmering stars, galaxies swirling in the void, and mysteries so profound they defy our understanding. This is the cosmic horizon, the edge of what we can see and comprehend. But what lies beyond it? What secrets does the universe hold that we have yet to uncover? Welcome to a journey through the 25 most baffling mysteries of the cosmic horizon, where science meets the unknown and curiosity leads us to the edge of reality itself. In this video, we'll explore the strange and the unexplained, from the gravitational enigma of the Great Attractor to the invisible force of dark energy that's tearing the universe apart. We'll dive into the questions that keep scientists awake at night, like why we haven't found extraterrestrial life yet, or what happens inside a black hole. Each mystery is a piece of a puzzle that could change how we see the cosmos and our place within it. So, are you ready to venture into the unknown? Let's begin. Now, let's turn our attention to one of the most intriguing mysteries in the cosmos, the Great Attractor. Imagine a force so powerful that it's pulling entire galaxies, including our own Milky Way, toward it at incredible speeds. This is the Great Attractor, a gravitational anomaly located roughly 250 million light-years away in the direction of the constellations Centaurus and Hydra. But here's the catch: we can't see it directly. Why? Because it lies hidden behind the dense plane of our own galaxy, obscured by stars, gas, and dust. This makes studying the Great Attractor incredibly challenging, like trying to spot a lighthouse through a thick fog. Scientists have had to rely on indirect observations, using radio waves and infrared light to peer through the Milky Way's veil. What they've found is both fascinating and puzzling. The Great Attractor seems to be part of a larger structure called the Laniakea supercluster, a vast network of galaxies bound together by gravity. But what exactly is causing this immense gravitational pull? Is it a supermassive cluster of galaxies, or could it be something even more exotic, like a concentration of dark matter? The truth is, we still don't know for sure, and that's what makes the Great Attractor one of the most compelling mysteries of the cosmic horizon, a cosmic tug-of-war that's reshaping our understanding of the universe's structure. Now, let's dive deeper into the Great Attractor's influence on the cosmos. This mysterious force isn't just pulling our galaxy, it's shaping the motion of countless others, creating a cosmic dance on an unimaginable scale. Picture this: galaxies, including our Milky Way, are being drawn toward the Great Attractor at speeds of hundreds of kilometers per second. This movement isn't random. It's part of a larger pattern that reveals the intricate web of the universe's structure. The Great Attractor sits at the heart of the Laniakea supercluster, a colossal network of galaxies spanning over 500 million light-years. Within this supercluster, galaxies flow like rivers toward the Great Attractor, much like water cascading toward a central basin. But what's truly fascinating is how this gravitational pull connects to the broader universe. It's not just about one anomaly, it's about how these forces weave together to form the cosmic tapestry we observe today. So, what could the Great Attractor be? One leading theory suggests it's a supercluster, a massive gathering of galaxies bound by gravity. These superclusters are some of the largest structures in the universe, and the Great Attractor might be one of the most significant. But there's another intriguing possibility: dark matter. Some scientists believe the Great Attractor's immense gravitational pull could be due to an enormous concentration of dark matter, the invisible substance that makes up most of the universe's mass. If true, this would mean the Great Attractor isn't just a collection of galaxies, but a dense, unseen force shaping the cosmos in ways we're only beginning to understand. As we continue to study this enigmatic phenomenon, one thing is clear: the Great Attractor is more than just a mystery. It's a key piece of the puzzle in understanding how the universe evolves and organizes itself. And as we unravel its secrets, we're not just learning about a distant anomaly, we're uncovering the very fabric of the cosmos. Next, we'll explore another cosmic enigma that challenges our understanding of the universe, the elusive nature of dark matter. Now, let's shift our focus to one of the most perplexing mysteries in modern astrophysics, dark matter. Unlike the Great Attractor, which we can observe indirectly through its gravitational effects, dark matter is entirely invisible. It doesn't emit, absorb, or reflect light, making it impossible to see with telescopes. Yet, despite its elusive nature, dark matter is believed to make up about 85% of all the matter in the universe. So, how did we even discover something we can't see? The story begins in the 1930s when astronomer Fritz Zwicky noticed something strange about the Coma cluster, a group of galaxies millions of light years away. He observed that the galaxies were moving so fast that they should have flown apart unless there was some unseen mass holding them together. This invisible glue became known as dark matter. But dark matter's influence doesn't stop at galaxy clusters. It plays a crucial role in holding individual galaxies together too. Imagine a galaxy as a spinning carousel. The stars on the outer edges should, in theory, move slower than those near the center. But observations show that stars on the outskirts move just as fast, if not faster. This can only happen if there's a massive amount of unseen matter surrounding the galaxy, providing the extra gravitational pull needed to keep everything in place. Without dark matter, galaxies as we know them simply wouldn't exist. Despite its critical role, dark matter remains one of the greatest unsolved puzzles in science. The challenge lies in its invisibility. Scientists have tried countless ways to detect it directly, from deep underground experiments shielded from cosmic rays to sophisticated detectors in space. Yet so far, no one has been able to capture a definitive signal. This has led to a fascinating question. Is dark matter made of particles we haven't discovered yet, or is it something entirely different? Theories abound, from weakly interacting massive particles, or WIMP, to actions, hypothetical particles that could solve multiple cosmic mysteries at once. But until we find direct evidence, dark matter remains a shadowy enigma. As we continue to explore the cosmos, dark matter serves as a reminder of how much we still have to learn. It's not just a missing piece of the puzzle. It's a fundamental part of the universe that shapes everything from the smallest galaxies to the largest structures in existence. And as we turn our attention to the next mystery, we'll explore another invisible force that's even more mysterious: dark energy, the mysterious power driving the universe's accelerating expansion. Now, let's take a closer look at the leading theories that attempt to explain the nature of dark matter. One of the most widely discussed candidates is something called weakly interacting massive particles, or WIMP for short. These hypothetical particles are thought to be heavy, slow-moving, and interact with ordinary matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Scientists believe WIMP could have formed in the early universe, and if they exist, they might be all around us, passing through Earth and even our bodies without us ever noticing. Another intriguing possibility is actions, particles that were originally proposed to solve a completely different problem in particle physics. Unlike WIMP, actions are predicted to be extremely light, almost ghost-like, and could interact with electromagnetic fields in subtle ways. Some experiments are now searching for these elusive particles by looking for tiny changes in magnetic fields or light, hoping to catch a glimpse of their presence. To test these theories, scientists have turned to some of the most advanced tools in modern physics. The Large Hadron Collider, the world's most powerful particle accelerator, is at the forefront of this search. By smashing particles together at nearly the speed of light, researchers hope to create conditions similar to those just after the Big Bang, potentially producing dark matter particles that could be detected indirectly. While no definitive evidence has been found yet, the search continues with new experiments and technologies being developed to push the boundaries of what we know. Beyond WIMP and actions, there are other, more exotic ideas. Some scientists propose that dark matter could be made up of primordial black holes, tiny remnants from the early universe. Others suggest it might involve particles from extra dimensions or even modifications to the laws of gravity itself. Each theory offers a unique perspective, but all share one thing in common. They challenge our understanding of the universe and push us to think beyond the limits of current science. As we explore these possibilities, it's clear that dark matter is more than just a scientific mystery. It's a gateway to uncovering the fundamental nature of reality. And while we may not have all the answers yet, the pursuit of dark matter continues to inspire groundbreaking discoveries, reminding us that the cosmos is full of surprises waiting to be revealed. Next, we'll turn our attention to another invisible force shaping the universe: dark energy, the mysterious power driving the cosmos apart at an ever-increasing rate. Now, shifting our gaze to another invisible force shaping the cosmos, we encounter dark energy, a mysterious phenomenon that's not only expanding the universe but doing so at an ever-increasing rate. Unlike dark matter, which pulls things together through gravity, dark energy seems to be doing the opposite, pushing the universe apart. This discovery came as a shock to scientists in the late 1990s when they observed distant supernovae, the explosive deaths of stars appearing dimmer than expected. These observations suggested that the universe wasn't just expanding, as Edwin Hubble had shown decades earlier, but that its expansion was speeding up. This revelation turned our understanding of the cosmos on its head, introducing dark energy as the dominant force driving this acceleration. So, what exactly is dark energy? The truth is, we don't fully know. One leading idea is that it's a property of space itself, often referred to as the cosmological constant, a concept first proposed by Albert Einstein. According to this theory, empty space isn't truly empty but has an inherent energy that causes it to expand. Another possibility is that dark energy is a dynamic field, similar to the Higgs field, but with properties that cause it to exert a repulsive force. Whatever its true nature, dark energy makes up about 68% of the universe's total energy content, dwarfing both dark matter and ordinary matter combined. The implications of dark energy are profound, especially when it comes to the ultimate fate of the universe. If dark energy's strength remains constant, the universe could continue expanding forever, leading to a scenario known as the Big Freeze, where galaxies drift so far apart that the cosmos becomes a cold, dark, and lonely place. On the other hand, if dark energy grows stronger over time, it could result in the Big Rip, tearing apart galaxies, stars, and even atoms themselves. These possibilities highlight just how much is still unknown about this enigmatic force and its role in shaping the cosmos. As we continue to study dark energy, new missions and telescopes are being developed to probe its effects with greater precision. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map the universe's expansion in unprecedented detail, offering clues that could help us unravel this cosmic mystery. While dark energy remains one of the greatest puzzles in modern science, its discovery reminds us that the universe is far more dynamic and mysterious than we ever imagined. Next, we'll explore how dark energy ties into the broader question of the universe's ultimate destiny and what it means for the future of everything we know. Now, let's turn our attention to what dark energy means for the ultimate fate of the universe. If dark energy continues to dominate, the cosmos could face one of two dramatic endings: the Big Rip or the heat death. The Big Rip scenario suggests that if dark energy's repulsive force grows stronger over time, it could eventually overcome all other forces in the universe. Galaxies would be torn apart, followed by stars, planets, and even atoms themselves, leaving the universe as a chaotic sea of disconnected particles. On the other hand, if dark energy's strength remains constant, the universe might experience a slower, colder demise known as the heat death. In this scenario, the universe would continue expanding, but galaxies would drift so far apart that stars would burn out, and the cosmos would become a vast, dark, and lifeless void. The debate among cosmologists centers on whether dark energy's strength is truly constant or if it could change over time. Some theories propose that dark energy might weaken, potentially allowing gravity to regain dominance and slow the universe's expansion. Others suggest it could grow stronger, accelerating the expansion even further. This uncertainty makes dark energy one of the most tantalizing mysteries in modern cosmology. To unravel it, scientists are analyzing data from projects like the Dark Energy Survey and preparing for future missions like the Euclid Space Telescope, which aim to measure the universe's expansion with unprecedented precision. What makes this debate so fascinating is that it's not just about understanding dark energy, it's about understanding the destiny of everything we know. Will the universe end in a dramatic big rip, or will it fade into a cold, silent heat death? Or could there be another outcome we haven't even imagined yet? These questions remind us that the cosmos is full of surprises, and dark energy is at the heart of one of the most profound mysteries of all. Next, we'll explore another cosmic enigma that challenges our understanding of the universe, the Fermi Paradox, and the question of why we haven't found extraterrestrial life. Shifting our gaze from the mysteries of dark energy, we now confront one of the most perplexing questions in the search for extraterrestrial life, the Fermi Paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox highlights the contradiction between the high probability of alien civilizations existing in the universe and the complete lack of evidence for their existence. Given the sheer size of the cosmos, with its hundreds of billions of galaxies and trillions of stars, it seems almost impossible that we are alone. Yet, despite decades of searching, we've found no definitive signs of intelligent life beyond Earth. One possible explanation is that intelligent life is incredibly rare. The conditions necessary for life to emerge, evolve, and develop advanced technology might be so specific that they occur only once in a great while. Earth, in this view, could be a cosmic fluke, a rare oasis of life in an otherwise barren universe. Another possibility is that intelligent civilizations do exist, but they are simply too far away for us to detect. The vast distances between stars and galaxies could mean that even if alien civilizations are out there, their signals or presence might never reach us. Alternatively, the limitations of our own technology could be a factor. Our current methods of searching for extraterrestrial life, such as scanning for radio signals or looking for biosignatures on distant planets, might be too primitive to detect advanced civilizations. It's possible that alien societies communicate in ways we can't yet understand or use technologies that are beyond our current comprehension. Some scientists even suggest that advanced civilizations might deliberately avoid contact, either to protect us or to protect themselves. The Fermi Paradox forces us to confront not just the question of whether we are alone, but also the nature of life and intelligence in the universe. Are we truly unique, or is the cosmos teeming with life that we simply can't see? As we continue to explore the stars, this paradox remains one of the most compelling mysteries of the cosmic horizon. Next, we'll delve deeper into the possible solutions to the Fermi Paradox and explore the theories that attempt to explain why we haven't found extraterrestrial life yet. Now let's dive deeper into the possible solutions to the Fermi Paradox, a question that continues to baffle scientists and stargazers alike. One of the most intriguing explanations is the Great Filter theory. This idea suggests that there's some kind of barrier or filter that prevents civilizations from reaching a stage where they can communicate across the stars or travel between galaxies. The chilling part, this filter might lie ahead of us, not behind. In other words, it's possible that most civilizations, including ours, are destined to self-destruct before they can achieve interstellar travel. Whether through war, environmental collapse, or some other catastrophic event, the Great Filter could explain why we haven't encountered other advanced societies. Another fascinating possibility is that alien civilizations are intentionally avoiding us. This might sound like science fiction, but some scientists argue that advanced societies could have good reasons to stay hidden. For instance, they might fear the consequences of contact with less advanced species, or they might follow a policy of non-interference to avoid disrupting developing civilizations like ours. Think of it as a cosmic version of the prime directive from science fiction. Aliens might be out there, but they're choosing to remain silent. There's also the idea that we're simply looking in the wrong way. Our current methods of searching for extraterrestrial life rely heavily on detecting radio signals or biosignatures. But what if advanced civilizations have moved beyond these technologies? They might communicate using methods we can't yet detect, like quantum entanglement or other forms of advanced physics that are still beyond our understanding. It's like trying to find someone using a flashlight when they're communicating with lasers. We're just not equipped to see them yet. Finally, some theories suggest that we might be living in a cosmic zoo, where advanced civilizations are observing us but deliberately keeping their presence hidden. This idea, sometimes called the zoo hypothesis, proposes that aliens might be studying us from a distance, much like how we observe animals in the wild without interfering. If this is true, it raises even more questions. Are we being watched? And if so, what are they waiting for? The Fermi Paradox doesn't just challenge our understanding of the universe, it challenges our understanding of ourselves. Are we destined to overcome the Great Filter, or is it only a matter of time before we face our own extinction? Could we be surrounded by civilizations that are simply too advanced for us to notice? As we continue to explore the cosmos, these questions remind us that the search for answers is as much about looking outward as it is about looking inward. Next, we'll turn our attention to another cosmic mystery, the enigmatic fast radio bursts and what they might tell us about the universe. Now, let's shift our focus to one of the most puzzling phenomena in the cosmos, fast radio bursts, or FRB. These are incredibly brief but powerful bursts of radio waves that last just milliseconds, yet they release as much energy as the sun does in an entire day. First detected in 2007, these bursts have left scientists scratching their heads as they seem to come from deep space far beyond our galaxy. What makes them even more intriguing is that they appear randomly, making them incredibly difficult to predict or study. The origins of fast radio bursts remain a mystery, but scientists have proposed several theories. One possibility is that they come from highly magnetized neutron stars known as magnetars. These dense, spinning remnants of collapsed stars could produce the intense bursts of energy we detect as FRBs. Another theory suggests that FRBs might result from collisions between neutron stars or black holes, events so cataclysmic that they send shock waves of energy across the universe. There's even speculation that these bursts could be signals from advanced extraterrestrial civilizations, though this idea remains highly speculative and lacks concrete evidence. What makes FRBs so challenging to study is their fleeting nature. By the time astronomers detect one, it's already over, leaving behind only a faint trace of its existence. To make matters more complicated, most FRBs are one-time events, meaning they don't repeat. However, a few repeating FRBs have been discovered, offering scientists a rare opportunity to study them in more detail. These repeating bursts have provided some clues, but they've also raised new questions, such as why some FRBs repeat while others don't. Despite the challenges, advancements in technology are helping us get closer to understanding these cosmic enigmas. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have been instrumental in detecting more FRBs, while international collaborations are working to pinpoint their exact sources. Each new discovery brings us a step closer to unraveling the mystery of fast radio bursts, but for now, they remain one of the most tantalizing puzzles in the universe. As we continue to explore the cosmos, FRBs remind us just how much we still have to learn. They challenge our understanding of the universe and push the boundaries of what we thought was possible. Next, we'll delve into the theories surrounding these mysterious bursts and what they might reveal about the nature of our universe. Now, let's take a closer look at the leading theories behind fast radio bursts and the ongoing efforts to uncover their true nature. One of the most compelling explanations points to magnetars, highly magnetized neutron stars that spin rapidly and emit intense bursts of energy. These cosmic powerhouses could be responsible for the sudden, explosive signals we detect as FRBs. In fact, in 2020, astronomers observed an FRB originating from a magnetar within our own galaxy, providing the strongest evidence yet for this theory. However, not all FRBs fit this pattern, leaving room for other possibilities. Another intriguing idea involves collisions between neutron stars or black holes. These catastrophic events release enormous amounts of energy, potentially producing the brief but powerful radio bursts we observe. While such collisions are rare, they could explain why some FRBs appear to be one-time events. On the other hand, repeating FRBs, which send out multiple bursts over time, suggest a different mechanism at play. Some scientists propose that these repeating bursts could come from young, highly active neutron stars or even exotic objects like quark stars, which are still theoretical. Then there's the more speculative theory that FRBs could be signals from advanced extraterrestrial civilizations. While this idea captures the imagination, it's important to note that there's no direct evidence to support it. Most researchers believe natural astrophysical processes are far more likely explanations. Still, the possibility, however slim, keeps the conversation about FRBs as fascinating as ever. Recent advancements in technology are helping scientists narrow down the sources of these mysterious bursts. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have detected hundreds of FRBs, including both one-time and repeating events. These discoveries are allowing astronomers to map the distribution of FRBs across the universe and study their properties in greater detail. International collaborations are also underway to combine data from multiple observatories, creating a more comprehensive picture of where these bursts come from and what causes them. As we gather more data, new questions continue to emerge. For instance, why do some FRBs repeat while others don't? What causes the variations in their brightness and frequency? And could there be multiple types of FRBs, each with its own unique origin? These questions drive the ongoing search for answers, pushing the boundaries of our understanding of the cosmos. The study of fast radio bursts is a reminder of how much we still have to learn about the universe. Each new discovery brings us closer to solving this cosmic puzzle, but it also reveals just how complex and mysterious the cosmos truly is. Next, we'll explore another enigmatic signal from the depths of space, the WOW signal, a mysterious radio transmission that has captivated scientists and enthusiasts alike for decades. Now, shifting our gaze to another cosmic enigma, we arrive at the WOW signal, a mysterious radio transmission that has baffled scientists and sparked imagination since its discovery in 1977. Detected by the Big Ear Radio Telescope at Ohio State University, this signal stood out for its intensity and narrowband frequency, characteristics that made it a prime candidate for potential extraterrestrial origin. Lasting just 72 seconds, the signal was so remarkable that astronomer Jerry Amon circled it on the printout and wrote "WOW" next to it, giving the phenomenon its iconic name. What makes the WOW signal so intriguing is its unique profile. It was observed at a frequency of 1,420 MHz, a range known as the water hole, where hydrogen and hydroxyl molecules emit natural radio waves. This frequency is often considered a likely choice for interstellar communication, as it falls within a relatively quiet part of the radio spectrum, making it easier to detect artificial signals. Despite its promising characteristics, the signal has never been detected again, leaving scientists to wonder whether it was a fleeting message from an advanced civilization or simply a rare natural phenomenon. Over the years, numerous attempts have been made to explain the WOW signal. Some suggest it could have been caused by a passing comet or a reflection of Earth-based signals off space debris. However, these explanations fail to fully account for the signal's strength and narrowband nature. Others argue that it might have been a one-time burst from a distant star or an unknown astrophysical event. Yet, none of these theories have provided a definitive answer, leaving the WOW signal as one of the most compelling mysteries in the search for extraterrestrial intelligence. The significance of the WOW signal extends beyond its unexplained origin. It serves as a reminder of the challenges and possibilities in the search for life beyond Earth. While modern efforts like those of the Search for Extraterrestrial Intelligence or SETI have advanced significantly with more sensitive equipment and broader sky coverage, the WOW signal remains a tantalizing clue that we may not be alone in the universe. Its enduring mystery continues to inspire both scientific inquiry and public fascination, keeping the hope alive that one day we might receive a signal that changes everything. As we ponder the possibilities, the WOW signal stands as a testament to the vast unknowns of the cosmos. Its story invites us to keep looking, listening, and questioning as we explore the infinite mysteries of the universe. Next, we'll delve into the ongoing efforts to detect similar signals and the technological advancements that are bringing us closer to uncovering the truth behind these cosmic whispers. Turning our attention to the ongoing quest for answers, one of the most puzzling aspects of the WOW signal is its singularity. Despite decades of searching, no repeat signal has ever been detected, leaving scientists to grapple with the question of why. The challenge lies in the vastness of space and the limitations of our technology. Even with advanced tools, pinpointing a signal that lasted just 72 seconds, originating from an unknown location, is like searching for a needle in a cosmic haystack. The signal's fleeting nature suggests it could have been a one-time event, perhaps a rare burst of energy from a distant star or an advanced civilization sending a brief, intentional message. But without a repeat, the mystery only deepens. Modern efforts to detect similar signals have come a long way since the 1970s. The search for extraterrestrial intelligence, or SETI, has evolved significantly, leveraging cutting-edge technology to scan the skies with unprecedented precision. Projects like the Allen Telescope Array and Breakthrough Listen use highly sensitive instruments to monitor millions of radio frequencies simultaneously, covering vast swaths of the sky. These initiatives are designed to detect even the faintest signals, increasing the chances of finding something as extraordinary as the WOW signal. Yet, despite these advancements, the search remains daunting. The sheer scale of the universe means that even with improved technology, the likelihood of detecting a repeat signal is slim, especially if it was a rare or transient event. Another challenge lies in distinguishing artificial signals from natural phenomena. The universe is filled with radio waves emitted by stars, pulsars, and other celestial objects, making it difficult to isolate potential signs of intelligent life. SETI researchers must sift through enormous amounts of data, using sophisticated algorithms to identify patterns that could indicate an artificial source. This process is time-consuming and requires immense computational power, but it's a necessary step in the search for extraterrestrial intelligence, the WOW signal serves as a reminder of the importance of this work, as it represents one of the few instances where a signal seemed to defy natural explanations. As we continue to explore the cosmos, the search for repeats of the WOW signal remains a priority. Each new detection brings us closer to understanding whether we are alone in the universe or part of a larger cosmic community. The advancements in technology and methodology offer hope that one day we might uncover the truth behind this enigmatic signal. Until then, the WOW signal stands as a beacon of curiosity, urging us to keep listening to the whispers of the universe. Next, we'll explore another cosmic mystery that challenges our understanding of space and time: the Pioneer anomaly, an unexplained phenomenon that has puzzled scientists for decades. Now, let's shift our gaze to another enigma that has baffled scientists for decades: the Pioneer anomaly. This mysterious phenomenon revolves around the unexpected deceleration of the Pioneer 10 and Pioneer 11 spacecraft as they journeyed through the outer reaches of our solar system. Launched in the early 1970s, these spacecraft were designed to explore the outer planets and beyond. But as they ventured farther from Earth, something peculiar began to happen. Instead of continuing on their expected trajectories, both spacecraft experienced a tiny but consistent slowing down, as if an unseen force was gently tugging them back toward the sun. At first, scientists were puzzled. The deceleration was minuscule, just a fraction of a nanometer per second squared, but it was enough to defy the laws of physics as we understood them. According to Newton's laws of motion and Einstein's theory of general relativity, the spacecraft should have been coasting smoothly through space, unaffected by any significant forces. Yet the data showed a clear anomaly, one that couldn't be explained by known gravitational influences from the Sun, planets, or even the Kuiper belt. This discrepancy sparked a wave of curiosity and debate within the scientific community, as researchers scrambled to uncover the cause of this strange behavior. One of the earliest explanations proposed was that the anomaly might be due to a flaw in the spacecraft's design. Some speculated that heat radiating from the spacecraft's power systems could have created a tiny but measurable thrust, pushing the probes in the opposite direction of their motion. This idea gained traction because the Pioneer spacecraft were powered by radioisotope thermoelectric generators, which produced heat as a byproduct. However, detailed calculations and simulations showed that while heat radiation could account for some of the deceleration, it wasn't enough to fully explain the anomaly. This left scientists with more questions than answers. Another intriguing possibility was that the Pioneer anomaly might hint at a gap in our understanding of gravity itself. Could there be some unknown force at play, perhaps a modification to Einstein's theory of general relativity or even evidence of dark matter's influence? These ideas sparked intense debate, with some researchers proposing new theories to account for the anomaly. Yet, despite decades of investigation, no definitive explanation has been found, and the Pioneer anomaly remains one of the most tantalizing unsolved mysteries in space exploration. What makes this anomaly so fascinating is not just the mystery itself, but what it represents. It's a reminder that even with all our advancements in science and technology, there are still phenomena that defy our understanding. The Pioneer anomaly challenges us to question our assumptions about the universe and to keep pushing the boundaries of what we know. As we continue to explore the cosmos, anomalies like this serve as humbling reminders of how much we have yet to discover. Next, we'll delve into how scientists eventually attributed the anomaly to thermal radiation, but also why some still question this explanation and what it means for the future of space exploration. After years of meticulous analysis, scientists began to piece together a plausible explanation for the Pioneer anomaly, a thermal radiation. The spacecraft's radioisotope thermoelectric generators, which provided power by converting heat from decaying plutonium into electricity, also emitted heat in the form of infrared radiation. This heat wasn't perfectly uniform. It radiated more strongly in certain directions, creating a tiny but measurable force. Over time, this uneven radiation could have acted like a subtle push, slowing the spacecraft down in a way that matched the observed anomaly. This explanation seemed to fit the data, and for many, it brought a sense of closure to the mystery. However, not everyone was convinced. While thermal radiation could account for much of the deceleration, some researchers pointed out that the calculations didn't perfectly align with the observed data. There were still small discrepancies that couldn't be fully explained by heat alone. This lingering uncertainty led some to wonder if there might be more to the story. Could there be another force at play, one that we haven't yet discovered? Or does this anomaly hint at a deeper flaw in our understanding of physics? The debate over the Pioneer anomaly has far-reaching implications for future space missions. If thermal radiation is indeed the primary cause, engineers can design spacecraft to minimize its effects, ensuring more accurate trajectories for probes venturing into deep space. But if there's more to the anomaly, it could mean that our current models of gravity and motion are incomplete. This uncertainty drives scientists to keep exploring, refining their theories, and designing experiments to test the limits of our knowledge. What's truly remarkable about the Pioneer anomaly is how it highlights the iterative nature of science. Even when we think we've solved a mystery, there's always room for doubt, for new questions, and for deeper exploration. It's a reminder that the universe is full of surprises, and that every answer we find often leads to more questions. As we prepare for future missions to the outer solar system and beyond, the lessons learned from the Pioneer anomaly will continue to guide us, pushing the boundaries of what we know and inspiring us to keep searching for the truth. Next, we'll turn our attention to another mysterious region of our solar system, the Oort cloud, a vast and elusive sphere of icy objects that holds secrets about the origins of our cosmic neighborhood. Now, let's journey to the outermost edges of our solar system, where a mysterious and distant region known as the Oort cloud lies in wait. Unlike the planets, asteroids, or even the Kuiper belt, the Oort cloud is a vast spherical shell of icy objects that stretches far beyond the orbit of Neptune. It's thought to extend nearly halfway to the nearest star, making it one of the most remote and enigmatic parts of our cosmic neighborhood. But what exactly is the Oort cloud, and why does it hold such fascination for astronomers? The Oort cloud is believed to be the birthplace of long-period comets, those spectacular visitors that streak across our skies once every few centuries or even millennia. These comets, like the famous Hale-Bopp or Hyakutake, originate from the Oort cloud, where trillions of icy bodies orbit the Sun in a slow cosmic dance. Occasionally, the gravitational tug of a passing star or the collective pull of the Milky Way's disk nudges one of these objects inward, sending it on a journey toward the inner solar system. As it approaches the Sun, the ice begins to vaporize, creating the glowing coma and tail that make comets so breathtaking to observe. Despite its importance, the Oort cloud has never been directly observed. Its extreme distance, ranging from about 2,000 to 200,000 times the distance between Earth and the Sun, makes it nearly impossible to detect with current technology. The objects within the Oort cloud are also incredibly faint, reflecting very little sunlight, and they're spread out over such a vast area that spotting them is like trying to find a single grain of sand in a desert. For now, the Oort cloud remains a theoretical construct, supported by the behavior of long-period comets and our understanding of how the solar system formed. The Oort cloud is thought to be a relic of the early solar system, a frozen archive of the building blocks that came together to form the planets. As the giant planets like Jupiter and Saturn migrated outward billions of years ago, their gravity likely flung countless icy bodies into the distant reaches of space where they settled into the Oort cloud. This makes the Oort cloud a treasure trove of clues about the conditions and processes that shaped our solar system in its infancy. But the Oort cloud isn't just a time capsule, it's also a reminder of how much we still have to learn. Its existence challenges our ability to explore and understand the farthest reaches of our own cosmic backyard. Future missions and advancements in technology may one day allow us to glimpse this distant realm, but for now, the Oort cloud remains a tantalizing mystery, a shadowy frontier that beckons us to keep pushing the boundaries of our knowledge. Next, we'll explore another fascinating region of the outer solar system, the Kuiper belt, a closer but no less intriguing collection of icy worlds that holds its own secrets waiting to be uncovered. Now, let's turn our attention to the challenges of studying the Oort cloud and the exciting possibilities that future missions might bring. Despite its immense scientific value, the Oort cloud remains one of the most difficult regions of the solar system to explore. The sheer distance alone is staggering. It would take a spacecraft traveling at current speeds tens of thousands of years just to reach the inner edge of the Oort cloud. Even with the fastest propulsion systems we have today, such as those used by the Voyager probes, the journey would still span centuries. This makes sending a probe to the Oort cloud a monumental task, one that pushes the limits of our engineering and imagination. But the challenges don't stop there. The Oort cloud's objects are incredibly faint and spread out over an unimaginably vast area. Detecting them requires telescopes with extraordinary sensitivity, and even then, we're limited to observing only the largest or most reflective objects. The rest remain hidden in the darkness, their secrets locked away. To make matters more complicated, the Oort cloud's icy bodies are so far from the sun that they receive almost no warmth or light, making them difficult to study even if we could get close. These obstacles have kept the Oort cloud largely out of reach, but they've also inspired scientists to dream up innovative solutions. One idea that has gained traction is the concept of a dedicated mission to the Oort cloud, equipped with advanced instruments designed to study these distant objects up close. Such a mission would likely rely on next-generation propulsion technologies, such as solar sails or nuclear-powered engines, to drastically reduce travel time. Solar sails, for example, harness the pressure of sunlight to propel a spacecraft, offering a way to reach incredible speeds without the need for heavy fuel. While these technologies are still in their early stages, they hold the promise of making the Oort cloud accessible within a human lifetime. Another approach involves using telescopes with unprecedented resolution and sensitivity to observe the Oort cloud from afar. Projects like the James Webb Space Telescope and future observatories could provide new insights into the composition and behavior of these icy bodies, even if we can't send a probe to visit them directly. By studying the light reflected or emitted by Oort cloud objects, scientists hope to learn more about their origins and how they've evolved over billions of years. The potential rewards of exploring the Oort cloud are immense. By studying these ancient relics, we could uncover clues about the formation of the solar system and the processes that shape the planets. We might even find evidence of organic molecules or other ingredients for life, preserved in the deep freeze of space. The Oort cloud could also hold surprises we haven't even imagined, from exotic types of ice to entirely new classes of celestial objects. As we look to the future, the Oort cloud represents both a challenge and an opportunity. It's a reminder of how much we still have to learn about our own cosmic neighborhood and how far we've yet to go in our exploration of the universe. While the journey to the Oort cloud may be long and difficult, the knowledge we stand to gain makes it a goal worth pursuing. Next, we'll venture closer to home, to the Kuiper belt, where a different set of icy worlds awaits our discovery. Now, let's shift our gaze closer to home, to a region of our solar system that has captivated astronomers for decades, the Kuiper belt. This vast expanse of icy bodies lies just beyond Neptune, stretching out into the cold, dark reaches of space. It's a cosmic treasure trove, filled with remnants from the early days of our solar system, and it holds secrets that could rewrite our understanding of how planets form and evolve. The Kuiper belt was first proposed in the mid-20th century by astronomers who noticed that the solar system didn't just end with Neptune. They theorized that there must be a belt of objects orbiting the Sun beyond the gas giants, and in the early 1990s their predictions were confirmed. The discovery of the first Kuiper belt object, other than Pluto, marked a turning point in our understanding of the solar system's outer limits. Today, we know that the Kuiper belt is home to thousands of icy bodies, ranging from small chunks of rock and ice to dwarf planets like Pluto, which was reclassified as a Kuiper belt object in 2006. Pluto's connection to the Kuiper belt is particularly fascinating. Once considered the ninth planet, Pluto is now seen as one of the largest and most prominent members of this distant region. Its orbit, tilted and elongated, is characteristic of many Kuiper belt objects, hinting at a shared history. Studying Pluto and its neighbors has given us a glimpse into the chaotic early days of the solar system, when planets were still forming and collisions were common. These icy bodies are like time capsules, preserving the conditions and materials that existed over 4.5 billion years ago. But the Kuiper belt isn't just a relic of the past, it's also a dynamic region that continues to shape our understanding of the solar system. The orbits of some Kuiper belt objects are influenced by the gravitational pull of Neptune, while others exhibit strange behaviors that suggest the presence of unseen forces or even a hidden planet. This has led to the intriguing hypothesis of Planet 9, a hypothetical world lurking in the outer solar system, though its existence remains unconfirmed. What makes the Kuiper belt so important is its role as a window into the solar system's infancy. The icy bodies found here are thought to be relatively unchanged since their formation, offering scientists a chance to study the building blocks of planets. By analyzing their composition, we can learn about the processes that shaped the early solar system and how they led to the formation of worlds like Earth. Some Kuiper belt objects even contain organic molecules, raising the possibility that they may have played a role in delivering the ingredients for life to our planet. As we continue to explore the Kuiper belt, each new discovery brings us closer to unraveling the mysteries of our cosmic origins. From the reclassification of Pluto to the search for Planet 9, this distant region reminds us that there's still so much to learn about our own backyard. Next, we'll delve deeper into the Kuiper belt's most puzzling features, including the mysterious Kuiper cliff and the unusual orbits of some of its inhabitants. Now, let's turn our attention to some of the most baffling features of the Kuiper belt features that continue to puzzle scientists and spark new theories. One of the most intriguing mysteries is the so-called Kuiper cliff. This term refers to a sharp drop-off in the number of objects observed beyond a certain distance from the Sun. It's as if the Kuiper belt suddenly ends, leaving astronomers scratching their heads. Why does this cliff exist? Some suggest it could be the result of gravitational interactions with Neptune, which may have swept away objects in that region. Others propose that an unseen object, perhaps even the elusive Planet 9, could be responsible for this abrupt boundary. The Kuiper cliff remains one of the most compelling puzzles in our solar system, and solving it could reveal new insights into the forces shaping the outer reaches of our cosmic neighborhood. Another mystery lies in the unusual orbits of some Kuiper belt objects. While many follow predictable paths, others have orbits that are tilted, elongated, or even clustered in ways that defy easy explanation. For instance, a group of objects known as extreme trans-Neptunian objects have orbits that are highly inclined and stretched far beyond the typical Kuiper belt region. These peculiar orbits have led scientists to speculate about the presence of an undiscovered planet, Planet 9, whose gravity could be influencing these objects. While no direct evidence of Planet 9 has been found yet, the strange behavior of these distant bodies keeps the hypothesis alive and fuels ongoing searches. Theories about these anomalies are as varied as they are fascinating. Some researchers suggest that the unusual orbits could be remnants of a chaotic early solar system, when gravitational interactions between young planets and passing stars may have flung objects into strange paths. Others believe that the Kuiper belt might have been shaped by the migration of giant planets like Neptune, which could have scattered objects into their current positions. There's even the possibility that some of these objects are not native to our solar system at all. They could be interstellar visitors, captured by the sun's gravity during its journey through the galaxy. What makes these mysteries so captivating is their potential to rewrite our understanding of the solar system's history. The Kuiper belt is more than just a collection of icy debris. It's a dynamic region that holds clues to the forces that shaped our cosmic backyard. Every unexplained feature, from the Kuiper cliff to the odd orbits of distant objects, invites us to rethink what we know about the formation and evolution of planets. As we continue to explore this distant frontier, each discovery brings us closer to unraveling these cosmic enigmas. Next, we'll venture even further into the unknown, exploring the hypothetical realm of the multiverse and the questions it raises about the nature of reality itself. Now, let's shift our gaze beyond the boundaries of our solar system and even our universe as we explore one of the most mind-bending concepts in modern cosmology, the multiverse theory. This idea suggests that our universe might not be the only one. Instead, it could be just one of countless universes, each with its own unique set of physical laws and properties. Imagine a cosmic tapestry where every thread represents a different universe, some similar to ours, others wildly different. The multiverse theory challenges our understanding of reality itself, pushing the boundaries of what we thought was possible. The roots of this theory stretch back to the strange and counterintuitive world of quantum mechanics. In the early 20th century, scientists discovered that particles at the smallest scales behave in unpredictable ways, existing in multiple states at once until observed. This led to the idea of a quantum multiverse, where every possible outcome of a quantum event spawns a new universe. For example, if you flip a coin, one universe might exist where it lands on heads and another where it lands on tails. While this might sound like science fiction, it's a serious interpretation of quantum mechanics that has sparked decades of debate. Another pillar of the multiverse theory comes from string theory, a framework that attempts to unify all the forces of nature. String theory suggests that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. To make the math work, string theory requires extra dimensions beyond the 3 we experience, up to 10 or even 11 dimensions in some versions. These extra dimensions could house other universes, separated from ours by membranes or brains. In this view, our universe might be just one bubble in a vast cosmic foam, with other bubbles representing entirely different universes. Despite its intriguing possibilities, the multiverse theory remains highly speculative. One of the biggest challenges is that, by definition, other universes would be beyond our ability to observe or interact with directly. This makes it difficult to test the theory using traditional scientific methods. Critics argue that if a theory can't be tested, it might not belong in the realm of science at all. However, proponents point to indirect evidence such as anomalies in the cosmic microwave background, the afterglow of the Big Bang, that could hint at collisions between our universe and others. The multiverse theory also raises profound philosophical questions. If there are infinite universes, does that mean every possible version of reality exists somewhere? Could there be a universe where the laws of physics allow for time travel, or where life evolved in ways we can't even imagine? These questions stretch our imagination and challenge our understanding of existence itself. While the multiverse remains a topic of intense debate, it's a reminder of how much we still have to learn about the cosmos. Next, we'll dive deeper into the evidence, or lack thereof, that could support the existence of these parallel worlds. Now, let's turn our attention to the evidence, or lack thereof, that could support the existence of the multiverse. While the idea of parallel universes remains speculative, scientists have proposed several intriguing clues that might hint at their reality. One of the most compelling pieces of potential evidence comes from the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. In this ancient light, researchers have detected strange anomalies such as cold spots and unusual patterns that don't quite fit our current understanding of the universe. Some theorists suggest these irregularities could be the result of collisions between our universe and neighboring ones, leaving behind cosmic fingerprints in the CMB. While this interpretation is far from proven, it offers a tantalizing possibility that we might one day find proof of other universes hidden in the oldest light we can observe. Another line of evidence often cited in discussions of the multiverse is the fine-tuning of the physical constants that govern our universe. These constants, like the strength of gravity or the charge of an electron, are precisely calibrated to allow for the existence of stars, planets, and life itself. If any of these values were even slightly different, the universe as we know it wouldn't exist. This remarkable precision has led some scientists to propose that our universe is just one of many, each with its own set of physical laws. In this view, the fine-tuning isn't a coincidence but a consequence of the multiverse, a vast array of universes where only those with the right conditions can support life. While this idea is still debated, it offers a potential explanation for one of the deepest mysteries of cosmology. Beyond the scientific evidence, the multiverse theory also raises profound philosophical questions. If there are infinite universes, does that mean every possible version of reality exists somewhere? Could there be a universe where the laws of physics allow for time travel, or where life evolved in ways we can't even imagine? These questions stretch our imagination and challenge our understanding of existence itself. They also force us to confront the limits of human knowledge. If other universes exist beyond our ability to observe or interact with, how can we ever truly know they're there? This uncertainty has led some to argue that the multiverse theory, while fascinating, might lie outside the realm of science altogether. Despite these challenges, the multiverse remains a topic of intense interest and debate. It pushes the boundaries of what we thought was possible, inviting us to consider the vastness of reality in ways that are both humbling and exhilarating. Whether or not we ever find definitive evidence for parallel universes, the multiverse theory reminds us of how much we still have to learn about the cosmos. Next, we'll explore another cosmic mystery that has puzzled scientists for decades: the Big Bang, the event that started it all. Now, let's journey back to the very beginning, the moment that set the stage for everything we know. The Big Bang is the cornerstone of modern cosmology, the event that birthed our universe approximately 13.8 billion years ago. But what exactly was the Big Bang, and how do we know it happened? The evidence is all around us, written in the fabric of the cosmos itself. One of the most compelling pieces of proof comes from the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. This ancient light, discovered in the 1960s, fills the entire universe and provides a snapshot of what the cosmos looked like just 380,000 years after its birth. The CMB's uniformity and slight temperature variations offer a powerful confirmation of the Big Bang theory, showing how the universe expanded and cooled over time. But the Big Bang isn't just about the beginning, it's also about the questions it leaves unanswered. For instance, what triggered the Big Bang in the first place? What existed before it, if anything? These are some of the most profound mysteries in science, and they challenge our understanding of time, space, and existence itself. Some theories suggest that the Big Bang wasn't a singular event but part of a larger cycle, with universes expanding and contracting in an endless loop. Others propose that our universe is just one bubble in a vast multiverse, each with its own Big Bang. While these ideas are still speculative, they highlight how much we still have to learn about the origins of everything. Another mystery tied to the Big Bang is the nature of the universe's initial expansion. In its earliest moments, the universe underwent a rapid period of growth known as inflation, stretching from a tiny point to an unimaginably large size in a fraction of a second. But what caused this inflation, and why did it stop? Scientists have yet to find definitive answers, though they continue to search for clues in the CMB and other cosmic phenomena. These unanswered questions remind us that the Big Bang isn't just a historical event, it's a gateway to understanding the fundamental nature of reality. As we reflect on the Big Bang, it's impossible not to marvel at how far we've come in unraveling the story of our universe. Yet, for every answer we find, new questions emerge, pushing the boundaries of human knowledge. Next, we'll delve into what might have existed before the Big Bang, exploring theories that take us even further into the unknown. Now, let's take a step even further back beyond the Big Bang itself. What could have existed before the universe as we know it began? This question might seem impossible to answer, but scientists have proposed some fascinating theories that push the boundaries of our imagination. One such idea is the concept of the Big Bounce. This theory suggests that our universe isn't the result of a single, isolated event, but part of an endless cycle of expansion and contraction. Imagine the universe like a cosmic rubber band, stretching out and then snapping back over and over again. In this scenario, the Big Bang wasn't the beginning of everything. It was simply the latest chapter in an infinite story of cosmic rebirth. Another intriguing possibility is the multiverse theory. If our universe is just one of many, each with its own Big Bang, then what we call the beginning might be just one moment in a much larger, more complex reality. Picture a vast ocean of universes, each bubbling into existence, expanding and evolving independently. Some scientists believe that collisions between these universes could even leave traces in the cosmic microwave background, offering clues to their existence. While these ideas are still speculative, they open up a breathtaking perspective on the nature of reality itself. Then there's the idea of quantum fluctuations. In the strange world of quantum mechanics, particles can pop in and out of existence seemingly out of nowhere. Some researchers propose that the Big Bang could have been triggered by a similar quantum event, a tiny fluctuation in an otherwise empty void that grew into the universe we see today. This theory suggests that even nothingness might not be truly empty, but a fertile ground for the birth of new realities. Of course, these theories raise as many questions as they answer. If the Big Bounce is real, what sets the rhythm of this cosmic dance? If the multiverse exists, how do these universes interact, if at all? And if quantum fluctuations are the key, what governs their behavior? These questions remind us that the mysteries of the cosmos are as deep as they are endless. As we ponder what might have come before the Big Bang, we're reminded that the universe is full of surprises. Every discovery leads to new questions, and every theory opens doors to uncharted territories. Next, we'll explore another cosmic enigma: black holes, those mysterious regions of space-time where gravity reigns supreme. Now, shifting our gaze to one of the most captivating and enigmatic phenomena in the cosmos, we arrive at black holes. These mysterious regions of space-time are places where gravity is so incredibly strong that nothing, not even light, can escape their pull. Imagine a cosmic vacuum cleaner, but one so powerful that it warps the very fabric of reality around it. Black holes are born from the dramatic deaths of massive stars. When such a star exhausts its fuel, it collapses under its own gravity, creating a point of infinite density known as a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. But black holes are more than just cosmic vacuum cleaners. They are laboratories for testing the limits of our understanding of physics. For instance, their immense gravity bends light and distorts time, creating effects that seem straight out of science fiction. Near a black hole, time slows down dramatically, a phenomenon known as time dilation. If you were to watch someone fall into a black hole from your perspective, they would appear to freeze at the event horizon, never quite crossing it. Yet, from their perspective, they would pass through the horizon in an instant, pulled inexorably toward the singularity. One of the most fascinating aspects of black holes is their ability to grow. They can devour nearby matter, growing larger and more powerful over time. Supermassive black holes, which can weigh millions or even billions of times more than our Sun, often reside at the centers of galaxies, including our own Milky Way. These cosmic giants play a crucial role in shaping the structure of galaxies, influencing the motion of stars and gas around them. Yet, for all we know about black holes, they remain shrouded in mystery. What happens inside the event horizon? What lies at the singularity? These questions push the boundaries of our knowledge, challenging us to rethink our understanding of space, time, and the very nature of reality. As we continue to explore these cosmic enigmas, we uncover not just answers, but new questions that deepen the wonder of the universe. Next, we'll delve into one of the most perplexing puzzles surrounding black holes, the information paradox, a question that has puzzled scientists for decades and continues to spark debate and discovery. Now, let's turn our attention to one of the most baffling questions in modern physics, the black hole information paradox. At its core, this paradox challenges one of the fundamental principles of quantum mechanics, the idea that information cannot be destroyed. When an object falls into a black hole, it seems to vanish forever, taking all its information with it. But if information is truly lost, it contradicts the laws of physics as we understand them. This dilemma has puzzled scientists for decades, and it all began with a groundbreaking discovery by Stephen Hawking. Hawking proposed that black holes aren't entirely black. Instead, they emit a faint radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate over time. But here's the catch: this radiation appears to carry no information about the matter that fell into the black hole. If the black hole evaporates completely, where does that information go? This question sparked a heated debate, with some physicists arguing that the information is irretrievably lost, while others insisted it must somehow be preserved. In recent years, however, new theories have emerged that might help resolve this paradox. One leading idea is that the information isn't lost but is instead encoded in the Hawking radiation itself, albeit in a highly scrambled form. This concept, known as the firewall hypothesis, suggests that the event horizon might not be as smooth as once thought. Instead, it could be a chaotic, high-energy boundary that scrambles and preserves information as it escapes. Another intriguing proposal is the idea of holography, which suggests that all the information about what falls into a black hole is stored on its surface like a cosmic hologram. This theory ties into the broader concept that our universe might itself be a hologram, with all its information encoded on a two-dimensional surface. Recent breakthroughs, including advancements in string theory and quantum gravity, have brought us closer to understanding how information might escape a black hole. For instance, the discovery of soft hair, low-energy particles on the event horizon, has provided a potential mechanism for storing information. While these ideas are still theoretical, they offer hope that the paradox might one day be resolved. The black hole information paradox isn't just a scientific curiosity, it's a gateway to deeper questions about the nature of reality itself. What happens to information in the most extreme environments? How do the laws of quantum mechanics and gravity reconcile? As we continue to explore these questions, we're not just solving a puzzle, we're uncovering the very fabric of the universe. And with each discovery, we inch closer to understanding the cosmos in ways we once thought impossible. Next, we'll explore another cosmic mystery that flips the script on black holes, white holes, the theoretical opposites that might hold the key to even greater secrets of the universe. Now, let's shift our focus to a concept that feels like it's straight out of science fiction: white holes. Imagine a black hole, but in reverse. While black holes pull everything in, never letting anything escape, white holes are theorized to do the exact opposite. They're thought to be cosmic fountains, spewing out matter and energy instead of swallowing them. But here's the catch: white holes have never been observed, and their existence remains purely hypothetical. So, what makes them such a fascinating idea, and why do scientists even consider them a possibility? To understand white holes, we need to revisit the equations that describe black holes. In the early 20th century, physicist Carl Schwarzschild found solutions to Einstein's equations of general relativity that predicted the existence of black holes. But those same equations also hinted at the possibility of white holes, regions of spacetime where matter and energy could only flow outward, never inward. While black holes are formed from the collapse of massive stars, white holes would require a completely different origin, one that defies our current understanding of physics. One of the most intriguing aspects of white holes is their connection to the concept of time reversal. In theory, a white hole could be seen as a black hole running backward in time. If you were to rewind the process of a black hole's formation, you might end up with something resembling a white hole. This idea has led some scientists to speculate that white holes could be the other end of black holes, connected by a theoretical tunnel through spacetime known as a wormhole. But before we get too excited, it's important to note that wormholes are also purely hypothetical, and no evidence for them has ever been found. So why do white holes matter if they're just theoretical? For one, they challenge our understanding of the universe's most extreme environments. If white holes exist, they could provide clues about the nature of space-time, the behavior of matter under extreme conditions, and even the origins of the universe itself. Some theories suggest that the Big Bang itself could have been a kind of white hole, with the universe exploding into existence from a single point. While this idea is speculative, it highlights the potential role white holes could play in solving some of cosmology's biggest mysteries. Despite their allure, white holes face significant challenges. For one, they violate the second law of thermodynamics, which states that entropy or disorder always increases over time. A white hole, by definition, would decrease entropy, making it seem impossible under our current laws of physics. Additionally, no observational evidence supports their existence, and they remain a topic of debate among scientists. Some argue that white holes are simply mathematical curiosities with no physical reality, while others believe they could exist in regions of the universe we have yet to explore. As we continue to push the boundaries of our understanding, white holes remind us that the universe is full of surprises. They challenge us to think beyond what we know and to explore the limits of our imagination. Whether they exist or not, the concept of white holes opens up new avenues for discovery, inviting us to question the very fabric of reality. And as we'll see next, this idea of cosmic opposites doesn't stop here. White holes might even hold the key to understanding wormholes and the mysteries of spacetime itself. Now, let's take a closer look at how white holes might be connected to one of the most mind-bending concepts in physics: wormholes. If white holes are the cosmic fountains spewing out matter and energy, wormholes could be the tunnels that link them to black holes, creating a bridge through spacetime. Imagine a shortcut across the universe where you could travel from one point to another in an instant, bypassing the vast distances of space. This is the tantalizing idea behind wormholes, and white holes might just be the key to understanding how they could work. The connection between white holes and wormholes comes from the same equations that predicted their existence. In the framework of general relativity, a wormhole, also known as an Einstein-Rosen bridge, is a theoretical passage through spacetime that could connect two distant points. If a black hole and a white hole were linked by such a tunnel, it would create a pathway where matter could travel from one region of the universe to another. This idea has captured the imagination of scientists and science fiction writers alike, offering a potential solution to the problem of interstellar travel. But here's the catch: wormholes are incredibly unstable. According to our current understanding of physics, they would collapse almost instantly under the weight of their own gravity. To keep a wormhole open, you'd need something called exotic matter, a hypothetical substance with negative energy that could counteract the gravitational forces trying to close the tunnel. The problem is, exotic matter has never been observed, and its existence remains purely speculative. Without it, wormholes would be nothing more than a fleeting mathematical possibility. Another challenge is the sheer scale of the forces involved. The energy required to create and sustain a wormhole would be beyond anything we can currently imagine. Even if we could harness such energy, the conditions inside a wormhole would be extreme, with tidal forces strong enough to tear apart anything that entered. This raises the question, even if wormholes exist, could anything actually survive the journey through one? Despite these challenges, the idea of wormholes continues to inspire research and exploration. Some scientists believe that quantum mechanics might hold the key to stabilizing wormholes, using phenomena like quantum entanglement to keep them open. Others suggest that wormholes could exist on microscopic scales, hidden within the fabric of spacetime itself. While these ideas are still in the realm of theory, they offer a glimpse into the possibilities that lie beyond our current understanding. The connection between white holes and wormholes also raises intriguing questions about the nature of spacetime. If wormholes do exist, they could provide a way to test some of the most fundamental principles of physics, from the behavior of gravity to the structure of the universe itself. They could even offer clues about the origins of the cosmos, suggesting that the universe might be more interconnected than we ever imagined. As we explore these ideas, it's important to remember that both white holes and wormholes remain unproven. They are fascinating concepts that push the boundaries of our knowledge, but they also highlight the limits of what we currently understand. Whether they exist or not, they remind us that the universe is full of mysteries waiting to be uncovered. And as we continue to probe the depths of space and time, who knows what other surprises might be waiting just beyond the horizon. Now, shifting our gaze from the mysteries of space-time to the search for life beyond Earth, let's explore one of the most intriguing tools in the quest to understand our place in the cosmos, the Drake equation. Developed by astronomer Frank Drake in 1961, this formula is an attempt to estimate the number of intelligent civilizations that might exist in our galaxy. At its core, the Drake equation is a way to frame the conversation about the likelihood of extraterrestrial life, breaking down the vast question into smaller, more manageable pieces. The equation itself is deceptively simple. It multiplies several factors together, each representing a step in the process of how life might arise and develop into intelligent, communicative civilizations. These factors include the rate at which stars form in the galaxy, the fraction of those stars with planetary systems, the number of planets in each system that could support life, the likelihood of life actually emerging on those planets, the probability of that life developing intelligence, the chance of intelligent life creating technology that could communicate across space, and finally, length of time such civilizations might last. While the equation provides a structured way to think about the problem, it's important to note that many of these factors are still unknown or highly uncertain. For example, we've only recently begun to discover exoplanets, and while we know many stars have planets, we're still learning how many of those planets might be habitable. Similarly, the step from simple life to intelligent, technologically advanced civilizations is a huge leap, and we have no way of knowing how common or rare that might be. This uncertainty is what makes the Drake equation so fascinating and so debated. Some scientists argue that the equation is too speculative, with too many unknowns to provide any meaningful estimate. Others see it as a valuable framework, a way to organize our thinking and guide future research. Over the years, estimates based on the Drake equation have ranged wildly, from just a handful of civilizations in the galaxy to millions. The truth is, we simply don't have enough data to say for sure. What the Drake equation does, however, is remind us of the profound questions we're trying to answer. Are we alone in the universe? If not, how common is life like ours? And if intelligent civilizations are out there, why haven't we heard from them? These questions drive the search for extraterrestrial intelligence, or SETI, and they continue to inspire both scientists and dreamers alike. As we ponder the possibilities, it's worth noting that the Drake equation isn't just about numbers, it's about perspective. It challenges us to think about the vastness of the cosmos and our place within it. And while we may not have all the answers yet, the journey to find them is one of the most exciting adventures in science. Next, we'll take a closer look at how modern discoveries, from exoplanets to extremophiles, are reshaping our understanding of the Drake equation and its variables. Stay with us as we dive deeper into this cosmic puzzle. Now, as we turn our attention to the evolving landscape of cosmic discovery, let's examine how modern science is reshaping our understanding of the Drake equation. Over the past few decades, breakthroughs in astronomy and biology have provided new insights into the variables that make up this iconic formula, offering both clarity and new questions. One of the most significant advancements has been the discovery of exoplanets, planets orbiting stars beyond our solar system. Since the first confirmed detection in 1992, thousands of exoplanets have been identified, with many residing in the so-called habitable zone, where conditions might allow liquid water to exist. This has dramatically improved our estimates of the fraction of stars with planetary systems and the number of potentially habitable worlds. What was once a speculative guess is now grounded in data, suggesting that planets capable of supporting life might be far more common than we once thought. But it's not just about finding planets, it's about understanding the conditions that make life possible. Enter extremophiles, organisms on Earth that thrive in environments once thought inhospitable, such as deep-sea hydrothermal vents, acidic hot springs, or even the frozen deserts of Antarctica. These discoveries have expanded our definition of habitability, showing that life can exist in a wider range of conditions than previously imagined. This has profound implications for the Drake equation, as it suggests that the likelihood of life emerging on other planets might be higher than we once assumed. Yet, even with these advancements, the equation remains shrouded in uncertainty. While we've made progress in understanding the early steps, like the formation of stars and planets, the later variables, such as the development of intelligent life and the longevity of civilizations, remain deeply speculative. For instance, we still don't know how often simple life evolves into complex, intelligent beings, or how long such civilizations might survive before collapsing or transcending their planetary origins. These gaps remind us that the Drake equation is less about providing definitive answers and more about guiding our exploration and framing the questions we need to ask. Another limitation lies in the equation's focus on our galaxy alone. While it's a useful starting point, the universe contains billions of galaxies, each potentially teeming with its own possibilities. This raises the question of whether the Drake equation should be expanded to account for the broader cosmos, or if it's better suited as a tool for understanding our immediate galactic neighborhood. Despite these challenges, the Drake equation remains a cornerstone in the search for extraterrestrial intelligence. It continues to inspire scientists to refine their methods, from improving telescope technology to developing new ways to detect biosignatures on distant worlds. It also serves as a reminder of how far we've come and how much further we have to go in our quest to understand whether we're alone in the universe. As we look to the future, the Drake equation will undoubtedly evolve alongside our discoveries. Each new exoplanet, each new extremophile, and each new insight into the origins of life brings us closer to answering the profound questions it poses. And while we may not yet have all the pieces of the puzzle, the journey to find them is as thrilling as the answers themselves. Next, we'll venture into another cosmic mystery that challenges our understanding of the universe, the enigmatic nature of black holes and the secrets they hold. Stay with us as we explore the depths of these gravitational giants. As we reach the end of our journey through the 25 mysteries of the cosmic horizon, it's clear that the universe is far more enigmatic and awe-inspiring than we could ever imagine. From the gravitational pull of the Great Attractor to the elusive nature of dark matter and dark energy, each mystery challenges our understanding of reality and pushes the boundaries of human knowledge. We've explored the Fermi Paradox and pondered the silence of the cosmos, marveled at the fleeting brilliance of fast radio bursts, and questioned the origins of the wow signal. We've ventured into the depths of black holes, speculated about the existence of white holes and wormholes, and even dared to imagine the possibility of a multiverse. Each of these mysteries reminds us that the universe is a vast, intricate puzzle, and we've only just begun to piece it together. These cosmic enigmas aren't just scientific curiosities, they're windows into the fundamental nature of existence. They challenge us to think bigger, to question our assumptions, and to embrace the unknown. Whether it's the search for extraterrestrial life, the quest to understand the origins of the universe, or the exploration of distant regions like the Oort cloud and the Kuiper belt, each mystery invites us to dream, to wonder, and to explore. They remind us that the cosmos is not just a place of stars and galaxies, but a realm of endless possibilities and profound questions. So, which of these mysteries captivates you the most? Is it the haunting silence of the Fermi Paradox, the explosive power of fast radio bursts, or the mind-bending implications of the multiverse theory? Let us know in the comments below. We'd love to hear your thoughts and spark a conversation about the wonders of the universe. And if you've enjoyed this cosmic journey, don't forget to hit the like button, subscribe to our channel, and ring the notification bell so you never miss an exploration into the mysteries of space. The universe is vast and there's so much more to discover. Together, let's keep exploring the unknown and uncovering the secrets of the cosmic horizon. Until next time, stay curious and keep looking up.